We're going to begin by walking through the 4 steps that we need to follow to find a general solution to a 2x2 system of differential equations that looks like this. dx dt is equal to ax plus by, and then dy dt is equal to cx plus dy. When you solve a system like this, the first thing you need to do is to write the system in matrix form. We're going to write it like this. The derivative of vector x with respect to time is equal to matrix A times vector x, where vector x is equal to xy, it's right up here, and matrix A, which is A, B, C, D, and that's right up there. Vector x right here is the solution to our system of differential equations. To find the solution form for x, what we're going to do is we're going to compare our system dx dt is equal to ax to the differential equation du dt is equal to lambda u. Now, these two are different, but their solution forms are similar. The solution to the differential equation du dt is equal to lambda u is equal to a constant c times e to the lambda t. Similarly, solutions to our system of equations dx dt is equal to a times x is going to be of the form x of t is equal to vector v times e to the lambda t. Lambda is the eigenvalue of matrix A, and then v is the eigenvector that is associated with that eigenvalue. Each eigenvalue lambda is going to produce a solution in this form right up there, and then the general solution of our system is going to be a linear combination of those individual solutions. The second step that we need to follow to find our solution x is to find the eigenvalues. To do that, we are going to solve the equation, the determinant of a minus lambda I is equal to 0, and we're going to solve that for lambda. If A is a 2x2 matrix, like the one that we're working with, alternatively, you can solve the equation lambda squared minus the trace of A times lambda plus the determinant of A is equal to 0. The trace of A is just when you add up the main diagonal elements in matrix A. In step 3, we're going to find the eigenvectors. An eigenvector v is a non-zero vector that satisfies this equation AV is equal to lambda v. If we move the lambda v to the left, that's equivalent to solving the system of equations a minus lambda I times v is equal to 0. And we'll solve that for v. The last step, step 4, is to write down the general solution. The form of the general solution is going to depend on what type of eigenvalue we got in step 2. It's going to be either distinct real, repeated, or complex. Let's look at the solution for case 1, where our eigenvalues are distinct real eigenvalues. So we're going to let lambda equal lambda 1 and lambda 2. Our solution then looks like this. Our v's are our eigenvectors, and then our lambdas are up in the exponent. The second case you can encounter is when lambda is a repeated eigenvalue. I just put down here that this is the case where lambda is equal to lambda. Here's what our solution looks like. We have one eigenvector v that appears in both of these terms. We have our eigenvalue up here in the exponent, and then we have a new vector that we're going to call vector w, and it is called a generalized eigenvector, and you find it by solving this equation. The last case is where we have complex eigenvalues, and we're going to let lambda equal alpha plus or minus beta times I. Here's what our solution looks like. Let's start with the exponent. Alpha is up here in the exponent, and then beta is in the trig functions. Now let's think about our eigenvector. Our eigenvector is vector v, and we have to split it up into its real part and its imaginary part. A is the real part, and it's right up here in our solution. And then B is the imaginary part, and it's right here in our solution.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.